Hello, welcome back to part two. My name's Stephen Bright. This is the second part of three videos. This is really the sort of middle section where we talk really for engineers, where we talk about the sort of detailed engineering analysis behind EasiBridge and how it works. So really aimed at engineers and students involved in engineering. Non-engineers could skip to video 3 where we explain more about what EasiBridge can do. So go back to the detail of what we talked about in video 1. EasiBridge really works in a combination of truss, bending and local bending. So in this slide, first of all, we talk about the sort of truss behaviour here. The rope's been in pure tension and the ladder's been subjected to a pure compression. So if we took a cut section through the middle bay, for instance, of this 18-meter span, if we took a cut section where we've shown the scissors there and that little animation, we've got a pure tension stress block in the ropes and we've got a pure tension stress block in the ladders. That's a uniform compressive stress block in the ladders due to this global truss behaviour. Sadly, the world is more complicated than that. We've also got to get these ladders to span locally between sort of node points where the mass or the end supports are. And what that does is establish this sort of local beam bending that we would normally be familiar with. Beam bending, compression on one side, tension on the other. So the sort of stress block we see in that ladder there would be that triangular stress distribution we see on the right-hand side, increasing tension generally on the top surface and increasing tension on the bottom surface, peaking on the outer fibres. As we mentioned previously, I believe, the mass on these structures tend to act a little bit like a spring support. They're not touching the ground, they're only sort of acting because they're mobilised by the ropes, and that tends to be a bit like a spring as far as the ladders are concerned. Now, in order to analyse or to check the adequacy of these structures, what we need to look at then are the combined effects of that truss behaviour, the global behaviour and that local bending behaviour. We need to add those two effects together and check the ladders are adequate. So if we look at that cut section again, down the bottom there we see that's what the ladder style looks like. First stress block on the left hand side is this uniform compression stress block due to those ladders being squeezed together as part of being a truss. Then we have that triangular stress block due to the local bending in that ladder, triangular opposite tension and compressive on opposite faces. If we combine those two together, what we find is the tension stresses tend to diminish, obviously because the truss compression tends to diminish that overall tension, but the compressive stresses are obviously additive. So we're really looking at stresses which are quite onerous in compression for those ladders. Now, when we're dealing with compression, most engineers will be familiar, we have to worry about things like buckling. So when things become long and slender or not stocky, members can buckle before they can fail in pure crushing. So the ladders in EasiBridge are certainly liable to that. We're talking about very long spans, very slender elements. So what we're broadly finding, it varies according to span, and there's all sorts of complicated variables going on, but roughly speaking, on the largest EasiBridges, we're talking about compressive strength reductions of around 90% due to the length of the ladders we're using. So these long lengths are critical, and that's the sort of upper bound that we're talking about, 90% reduction in their plane compressive strength. So what's the upshot of that when we do a load analysis on these bridges? For first of all, truss behaviour we see there at the top, that's the sort of compressive and tension axial loads that we're expecting. Then on the left hand side, that much more complicated local bending pattern, and this is a moving load, so that can be quite complicated, making sure we identify all the peaks. When we combine those stress effects together, that's a typical output for an 18-meter bridge. We find that local bending will predominate. Axial loads use up about 35% of the capacity of the section, but certainly the remainder, 3 times that generally, is used in local bending. That's for one particular alloy, not an alloy we use, but where we'd see that would fail a unity check. So for the ladders we use, that's a sort of background calculation that shows the relative order of magnitude of those two loads. And why is this important? Well, when we first conceived of EasiBridge, we always wanted to achieve an 18-meter span, and this is the sort of structure that an 18-meter span might have looked like without this analysis. So this was based on some very crude rule of thumbs as to limiting stresses and such like. that we thought would be relevant to the ladders. And to keep those stresses low, we were looking at concepts that involve triple stay, 3 masts on an 18-metre span, possibly bowstring outriggers to stabilise it. Certainly with the weight involved here, we'll be looking at a 4-person launch potentially with counterweight. Now, by using this spreadsheet and squeezing the absolute maximum we can out of these ladders, really understanding them much better at every point along the structure, analysing, refining and optimising quite intensely, we've got an 18-metre span back to something that looks like this on the bottom left-hand corner. A very simple structure, a twin stay, so light now, even at 18 metres, just 92 kilograms, a single operative can install that. So this really shows the benefits of investing in time and effort in engineering design, bringing a structure which might have looked like an electricity pylon down to something that looks much more like the sort of EasiBridge we know now. Another key thing with EasiBridge to get this to work are developing a lot of bespoke design features that are very unique to the system. So a bit more on that first. Well, first of all, because we're talking about local bending a lot in these ladders, we've had to develop bespoke ladders. These use swayed circular rungs. That's very important for this Virendale truss behaviour, the ladders on their side particularly. We've also got welded stiffener on each ladder section. Now that's important for rope attachments, but also important again for that Virendale truss behaviour to stiffen up that middle bay. So this is what a typical 10.5 metre EasiBridge kit looks like. Besides the ladders, first of all, we have a trolley. Obviously, I'm sure you noticed that. We have a nose girder at the front, which is vital for launch. We have a mast element which plugs into the ladders. Now that's shown there assembled before we drop it in. Obviously everything with EasiBridge is designed to be flat packed, so everything there comes apart extremely quickly. No bolted connections, it's all sprung and push fit connections to click everything together. We've then got advanced fibre ropes as well. We could use steel wire, but for portability and handling, we just find sort of composite type materials much better. So EasiBridge is based on sort of composite advanced fibre ropes. Critically though, there's 3 ladder types in every EasiBridge kit. We have end ladders, mid ladders and standard ladders. End ladders always go at the 2 end supports, very simple. They always form the beginning and end of every bridge. Mid ladder, also very simple. Wherever we're sitting a mast, which generally is in the middle of the section, we have a mid ladder that supports the mast. Everything else in between, very simple basic ladders. These are standard ladders. So we have many more standard ladders and other types, but every kit uses that 3 ladder pattern. Critical thing there, because of the number of ladders we're using, is the strength of the joint. So in an 18-metre bridge, we'd have 12 separate ladders. That's 11 joints, I believe. So we have to make sure that those joints are really stiff and rigid, and they also have to be very strong against these local bending loads that we still experience. So EasiBridge is based on 1.5 metre ladders, so we can easily carry them by personnel or quad. But making a joint that was sufficiently strong and particularly stiff, there was no flexibility. We looked at lots of concepts, so I won't dwell on this slide. This is sort of for a summary of post-tensioning type ideas at joints that we looked at in the early stages, and really that's what's carried through to the joint design we now use, the idea of post-tensioning those joints to make them very strong and stiff. Now this is what an EasiBridge joint looks like. We call them EasiLock joints. They have an end insert, first of all a male and female end insert to provide sort of shear transfer across the joint. Then we lock the system together with an over-center clamp. Now that really tensions that joint very hard, but what it also do is we mount it eccentrically. Now that's very important to give it bending strength in one direction only, and that's really is the basic premise of EasiBridge, is to make this thing strong in one direction. Now developing these joints sensibly, we can obviously throw very heavy, very robust connectors at this, but we want to make it as lean and as light as possible. So we've done destructive tests on our preferred joint type. Now we did it on earlier joints as well. But we've got that down to a joint which is now 95% the strength of the plain ladders, which really I think is the optimum, something that behaves just like the ladder but without being too big and cumbersome. Another key feature of EasiBridge is how we deal with variable spans. It would be so easy to design a bridge that just dealt with a 12-metre span, for example. That would be a dream. What EasiBridge has to do is deal with any span from 0 to 18 metres and do it sensibly and simply. So dealing with variable spans, what we do is obviously add more ladder sections to make up the span, but to accommodate simple details, what we've done is made the depth of each structure variable. So as we go from 6 meters here, from 10.5, that bridge is getting slightly deeper at each turn. We also critically use constant rope length. So every rope you see in all those pictures is about 9 meters long, never varies. The idea of that is there's no tension is required. So that a concern raised in the early days with ropes and ladders is somebody could, if we had a ratchet strap in there, for instance, and a tensioner, someone could over tension that and distort or damage the bridge. So what we've come up with here is a system where the bridge by gravity actually tensions itself. It's quite clever, and we won't go into that in detail, but basically it means that there's little or nothing the operators can set wrong and can destroy the bridge in building it, essentially. Next key feature is the trolley. Now the trolley is very important to get personnel across quickly and with a low profile, keeping their centre of gravity very low, very near the shear centre of the bridge. Another key thing you may have noticed with the trolley is we use it to launch the bridge into position. So it's a frictionless crossing, but also we use the trolley upside down to provide a frictionless launch roller as well. Another very useful spin-off of the trolley is this idea of using it for other applications, particularly this conveyor. So a little bit more on that in a minute. So in terms of how the trolley works, this little video we see here shows the bridge being launched. Now the key thing here is everything's inverted, and the difference, instead of when the person crosses, the trolley moves over the bridge. For launch, the trolley is static and the bridge moves. Now this allows us to achieve all installation from the home bank in near silence, and bridges can be recovered for reuse with the trolley almost as quickly as they're installed. Another key component is this nose girder. This is used for launch purposes. This is a bit of tapered aluminium fabrication, very special bit of fabrication, and what we then do is plug carbon fibre at extremely lightweight nose tubes to extend that. Now those carbon fibre tubes can extend anything up to 5 meters. Now that means we have an extremely lightweight sort of reaching component on the front that can reach between buildings particularly. It makes it very easy for the operator to launch this bridge. Another key feature of EasiBridge is its portability. We've always based the system on 1.5 meter ladders, so we can carry this thing pretty much anywhere, even inside building stairwells. Now that means we can use this thing for building crossings. We can even build bridges up to 12 meters long in a room as small as 2 meters. Again, that was something that was identified as critical in the early stages. Using short ladders means we can also come up with this handy infantry carrier system where we use short ladders, just plug a wheel into one of them, and we can then use that as a little trolley to carry an entire bridge around. So that's a 10.5 meter bridge being carried by a single operative. We can also use that wheeled carrier for other equipment, Bergens, ammunition and equipment, but also critically perhaps for casualty evacuation. Obviously ladders are very good for casualty evacuation anyway, but with this wheeled system we have the option that an evacuation will be done with just a single operative if need be. Finally, in this section, the other sort of unique feature of EasiBridge is we've designed it very much around quad bikes. So 1.5 meter ladders are very portable on a quad bike, but we've also designed EasiBridge that the entire live load capacity is based on quad bikes. So by putting 2 bridges side by side, we can start to carry quad bikes across gaps like this. Another spin-off of that being so lightweight is EasiBridge offers UAV placement, so remote autonomous placement, no personnel, where entire bridges can be flown in if necessary for both logistics and close support bridging. So that's a quick summary of the unique features of EasiBridge and obviously the engineering analysis. Part 3 will be more fun probably, where we look at what EasiBridge can do in general terms and what we hope it will do in the future. So I hope that was informative for engineers at least. Thank you very much for your time. More to follow. Thank you.